Good afternoon. Thank you all for joining us for this virtual lunch discussion this afternoon. I am pleased to introduce postdoctoral associate Vincent Sitzmann, who will be presenting today. And Vincent is also an incoming assistant professor at MIT beginning in 2022. Please feel free to ask questions for Vincent in the chat, and I will ask on your behalf throughout the presentation or at the end, whatever you're comfortable asking. And so please send those to me in the chat. And with that said, please take it away, Vincent.
Awesome. Thank you so much, Matt. Thanks also for the intro. Many of us started being in person again at MIT. We just started in-person events again. So this is actually interesting because this is a Zoom talk again, where most of the talks are now in person, but there's an advantage to this. And the advantage is that most of you are sitting in front of their desks. And that's great because I want to start out with a little interactive experiment. So if you would indulge me, you can join it. It's fun. It's very simple. What I want you to do is I want you to close your eyes and I want you to reach for something that is standing on your desk or on your desk. It might be your computer mouse. It might be your, I don't know, your a mug or something, and just lift it up. Okay, so the thing here is that most of you probably succeeded at doing that. And none of you are probably surprised. You can open your eyes again now if you have them closed. And that's something we do every day, and it's completely trivial to us, right? We just walk around, we pick stuff up, we interact with the world around us. But actually, I want you to take a pause for a moment and just think about how actually impressive that is that we can do that and how that works, right? Because in our head, we have two eyes. Our eyes constantly capture the equivalent of two videos, right? Just two 2D videos. And from these 2D observations that you capture constantly, your brain infers a representation of the environment around you that has an immense amount of information, right? For instance, it encodes the materials of things. It encodes the geometry of the environment around you, information about the appearance, how you have to grasp something, how heavy it will be, what material it's made out of. You remember, you could probably close your eyes and stand up and find the door, right? No problem. And we all do that just from 2D observations. And we learn this skill also basically mostly from 2D observations. And that is what we call a scene representation, right? Your brain has a representation of the scene that you're in. And now we can make that relevant to computer science, or rather it is very relevant to computer science. And for that, one just has to consider, for instance, these 6 applications of computer science here, right? There's like robotic grasping in the top left corner, or like manipulation. There's computer graphics, there's physics simulation, autonomous navigation and planning. What do all of these applications have in common? All of these applications have in common that they also need some representation of the underlying 3D scene. In grasping, you just went through that yourself. In graphics, you are trying to render a scene photorealistically, ideally. And for that, you also need a representation of the underlying 3D scene and so on. So how is this done today? Or how has this been done in the past? In the past, and still today, most of these applications are supported by what we call handcrafted scene representations. And what I mean by that is that the data structure, as well as the information that is stored in the data structure, is hand designed by humans. Right? How does that look like in graphics, for instance, in CGI in movies, or if you play video games? Usually that representation is a mesh representation, and that mesh stores information such as the albedo or the specular color. In manipulation, it might be a point cloud, or it might also be a mesh or a voxel grid, or who knows. Now, that's all good. What's the problem with that? The problem is that these representations were built and designed before before the current quote unquote age of AI, right? So what that means is that the algorithms that are around these representations are usually not differentiable. So they don't integrate well with modern machine learning algorithms. Also, these representations are hard to infer. So for instance, point clouds and inference means that you go from observations to the parameters of that representation. Point clouds, for instance, are just sets of points. It's kind of hard to predict sets of points with neural networks. It's not great. And lastly, and maybe most importantly, it seems that these representations aren't quite don't quite have the same level of generality than the thing that you have in your head. They don't represent all the properties of 3D scenes. They only represent the ones that we handcrafted into them. And with many of these representations, there is a question, how would we generalize them to have as much information as the thing that we just went through? Okay, so my research is about neural scene representations or learned scene representations. And what that means is that instead of handcrafting and hand engineering 3D representations, what we're trying to do is we're trying to learn these representations from data. So the goal is, given lots of data, can we learn algorithms that estimate these 3D representations, and then can we do something with these 3D representations? And this also connects back to the way computer vision is done today, right? So because what's the problem with the current approach to computer vision, right? So like we have an approach to computer vision, and most of you know this, that since 2012, basically, there has been this huge breakthrough in machine learning and in computer vision with convolutional neural networks. That was for computer vision. And in computer vision, that means that basically every task that is operating on images nowadays runs with these convolutional neural networks as a backbone. And that means things like image segmentation or depth prediction from images or object detection or classification, endless list. Everything that has to do with images is basically supported by these convolutional neural networks. So why does that not fit the bill? What's the problem here? The problem here is that these convolutional neural networks exactly lack these kinds of what we call inductive biases, both visual and physical, that make your scene representation work the way it does. For instance, convolutional neural networks do not understand 3D. They do not have a baked-in concept of 3D structure. And what that means in practice is, right, if I have my hand here and I move it closer to the camera, except for the fact that it gets blurry, for you, it's not any question that the thing that you're seeing is still my hand, and the hand is just moving closer, and then it's moving further away. From the perspective of a convolutional neural network, however, that's not the case. From the perspective of a convolutional neural network, as soon as the hand gets closer, it's basically a completely different image, because these convolutional neural networks do not have baked in the 3D structure of our world. So that's not great. And that is partly the reason why training these models requires such massive data sets. You can imagine that if every time you see, for instance, a car close to the camera or further away from the camera, that's kind of like a different image to the convolutional neural network, then that means that in your data set, you better have all of the different 3D positions and orientations of all the cars in your data set, right? And that's, of course, a problem, because that means we have to constantly collect these large data sets. And also, it means that once you have something in the real world later that is not in your data set, you're lost, right? So we hear about this from Tesla, for instance, right? Like how it has these glitches. And that is partly because of this. You basically do not have any guarantees on what happens when you get an image that is new from the perspective of you haven't seen that 3D configuration before. And lastly, that's exactly it. So so maybe some of you know this as the term of out of distribution generalization. So sometimes we say that, we have our training set, and then the problem is that if at test time we observe something that wasn't in our training set, then we have a problem. And that could, for instance, be 3D configurations. And today, if there's one thing that I can give you on your way today, is that there are, of course, people working on this, and I just want to give you the flavor of how solutions to these problems might look like. How can we teach 3D to neural networks? How can we teach neural networks to have a better understanding and structure of the 3D world around us? And for that, I want to start out with discussing one way how to actually think about a 3D scene in the first place. What actually is a 3D scene? Okay, so and for that, we're gonna take a little 2D example here. So this is a little example where we have gray, that's like free space or just nothing. Then there's 3 objects. There's the circle, the square, and the triangle, and we have a little coordinate system. And now the question is, how should we model mathematically this 3D scene? And the thing that I'm going to propose to you is to think about a 3D scene as a function. And that's just a fancy way of saying that this is going to be a thing, right? That you give a world coordinate. So you're going to give it a coordinate, and then that function is going to tell you what is at that coordinate. So for instance, all of the x coordinates in the blue triangle should be mapped to something that says I'm blue, I'm a triangle. All the x coordinates in the red square should be mapped to something that says I'm a square, and all the x coordinates in free space should be mapped to something that says I'm free space. So try to imagine this for the room that you're sitting in, right? So for the room that you're sitting in, that means that this room is a function, and that function maps, for instance, I don't know, this point here, in the case of my room, to air. There's just nothing here, right? And then, I don't know, if I put my finger on the desk, then that point should be mapped to something, I don't know, like wood or desk. Okay, so that is like a mathematical model. How can we actually implement this? Some of you might have heard about Voxel Grids. So Voxel Grids was one of the first approaches to modeling 3D structure in neural networks, or in this framework. And the reason why I'm bringing this up is because it's still popular and it's very easy to understand. A Voxel Grid basically takes 3D space, like the room that you're sitting in, and cuts it into little cubes. So imagine that it's like you have like a 3-dimensional table, if you wish, like a 3-dimensional grid that you lay into your room. And then every voxel, every one of these little cubes just stores whatever is in that cube, right? So if there's air, like nothing, then maybe the voxel is empty. And then if it's like including your desk, then maybe the voxel should say if there's a desk. And with voxel grids, we have made some cool progress. So for instance, we had a paper in 2018 where these voxel grids allowed us to do 3D reconstruction, subsequent novel view synthesis. So we were able to render novel perspectives of scenes. And you can see the results here. So always on the left-hand side, you can see renderings that are unobserved. So these are new perspectives of the scene. And on the right-hand side, you can always see the closest observation in the training set. There's problems with voxel grids though. And the big problem is basically that they scale very poorly. In fact, what you can imagine is for the room that you're sitting in, right? I'm sure there's many pretty small objects standing in the room around you. And if you stored the room naively as a voxel grid, if you parameterize it as a voxel grid, then you would need to make the voxels very small. And what that would mean is that you would need a very high resolution of the grid overall. And unfortunately, the memory complexity of this data structure scales with the side length of the voxel grid, and it scales cubically. And what that means is basically the room that you're sitting in, storing information about what is in each voxel is probably already computationally intractable and will be for the foreseeable future. And storing larger scenes in voxel grids is probably altogether infeasible. Also, yeah, as Matt said, please feel free to ask questions in between. So I'm just going to keep talking, but you can certainly interrupt. Okay, so how can we fix this little problem, right? So voxel grids, that won't work. Here's an idea. So this is what we're going to do is we're going to take that function that maps a coordinate to whatever is at that coordinate. And now we're going to parameterize that function as a neural network. In fact, a fully connected neural network. So let me talk a little bit about that. So this is a very unusual application of a neural network, if you wish. So if we think about this function a little bit, about really the continuous function that you would need to parameterize the room that you're sitting in, for instance, right? That function is very, very complicated. In fact, it's so complicated, there would be no way you could write it down, like on a piece of paper, right? Like, what would it be? I'm not sure if you, there's just no way. So in deep learning, one tool that we have are neural networks. And what neural networks are really, really, really good at is they are very good at fitting or regressing complicated functions. In fact, you can show that they can, in principle, parameterize any function. But in particular, what it turns out is that they're really, really good at parameterizing functions like this one. So this neural network is literally a neural network that takes in a 3D coordinate and outputs a feature representation, a learned vector, basically. And that learned vector is a code for whatever is at that 3D coordinate. And we wrote a paper on this in 2019. It's called Scene Representation Networks, and that was a presentation at NeurIPS. So now, what is cool, or like why is that parameterization reasonable? So the first thing is, similar to the voxel grid, it strictly enforces the 3D structure of our world. And what I mean by that is that the neural network takes a 3D coordinate as an input and it outputs something. So every 3D coordinate, there can only be one thing. This representation is by design respects the 3D structure of our world. And another really, really cool property of these representations is that they can be sampled anywhere and they can be sampled at arbitrary resolutions. And what I mean by that is that in contrast to the voxel grid, which is discrete, right, which basically discretizes space into this grid, into these little voxels, this is a continuous function. And you can sample this continuous function wherever you want. You can give it any 3D coordinate you want, and you can sample it at any arbitrary resolution. And that also means that the memory that this representation requires does not scale with the resolution you want to encode. And the way to think about this is, imagine you had a white wall. If you had a white wall and you wanted to represent that white wall as a voxel grid, then you would have to discretize it again, right? And you would have to regularly discretize it with whatever the resolution of your voxel grid is, and then that will cost memory. But if you had a continuous function, you could try to find a representation of the wall that has fewer parameters. For instance, you could parameterize it just as a plane, which is basically a normal vector, right? And then maybe the extent of the wall. And then it really doesn't matter at what resolution you want to store the wall, because you can just sample that continuous parameterization at whatever resolution you so wish. So the memory that this requires does not scale with the resolution you want to encode. It only scales with how complex your scene is. So if your scene is more complicated, then that function needs to be more complicated. Cool.
Hey, Vincent.
So yeah, go for it.
I just wanted to let you know, you have a gray box on the right side of the slide. I'm not sure if that's your computer or just intentional, but it's just some of the slides it's covering up some of the information. I just want to make sure.
Is it gone now?
Yes. Thank you so much.
Yeah, it's a little bit unfortunate. Zoom does this thing sometimes where basically if you have Zoom, if you have the Zoom controls, then it'll arrive. Yeah, well, okay, thanks for letting me know. So I guess I can't look at anyone's face.
No, there's now there was another one. Oh, there we go. Perfect. Thank you so much.
Okay, thanks for the hint. I appreciate it.
No worries.
Okay, so this is the little representation that we're going to use. And now there's a question of how can we actually train this representation, right? So how can we learn the weights of this representation? And the way we're going to do this is, or the key insight is, right, that unfortunately, even though we want to learn something about the 3D structure of our world, because that's so important, the only amount of data that we actually have access to at scale is 2D data. It's very expensive to collect ground truth 3D data, and it's not only expensive, it's also very hard. And it's very hard to do that at scale. The thing that is very easy is to collect variations of 2D data, and that could even be with 2D that includes things like even depth maps are not strictly speaking 3-dimensional. So basically anything that you can collect with running around with a camera is fine. So we have lots and lots of 2D data. So that's the thing that we want to use for training. So how do we do that? The way this is going to work, and unfortunately we won't have time to talk about this in detail because I want to talk about a few other things to just give you a little bit more inspiration. But the way these algorithms always work is that they take a set of 2D images that are generated by some 3D scene, right? Like the room that you're sitting in, if you took lots of pictures of that room, these pictures are, so to speak, generated by that underlying room. And then from these 2D pictures, you infer this 3D structured representation. And then how do we now supervise this, right? How can we learn this process? And the way we do that is we build a neural renderer. And a neural renderer is basically a function, right? That you basically give your 3D representation as an input. And then it allows you to place a camera anywhere in that 3D scene that is represented by that neural network. And then it allows you to render out that, that scene from that perspective. So it's basically a function that allows you to render your 3D structured representation from arbitrary viewpoints. And that's cool, because now what we can do is we can render out exactly the same observations that we have in the training set. And then we can just train this whole thing by comparing these renderings with whatever we gave our neural network as input. So we can train the whole thing end to end just with 2D observations. We don't need 3D observations. And that's the title of my talk, self-supervised scene representation learning. It's self-supervised because we only need images. And it's scene representation learning because the thing we're learning is the 3D representation of the scene. So I want to talk, just briefly give you an idea of how this neural renderer works. As I mentioned, I'm going to walk through this kind of quickly because there's maybe other things I'd like to talk about. But I just want to give you an idea of how these renderers look like, because the key insight here is they also need to respect the 3D structure of the representation. Okay, how does that work? Let's take a look at our simple scene here again, right? So this is our example scene. And now we want to place a camera in that scene, and we want to render the scene from this camera's perspective. And what we're going to do is we're basically going to shoot out rays from the camera, and we're going to look for wherever that ray intersects the geometry of the underlying 3D scene. Okay, how do we actually do that? What we're going to do is we're going to start on a ray close to the camera, and we're going to take the coordinate of that point on the ray. And then we're going to give that to our neural network, and we're going to ask it to give us the representation of whatever is at that coordinate. And then we're going to take that little learned representation, and we're going to give it to another neural network. And that neural network is going to predict a step length. And then we're going to advance along the ray according to that step length. So we're going to march along the ray. So now, of course, you can do that, right? Like nothing, we are in, rebuilding this model, we can do whatever you want. Why does this actually make any sense whatsoever? So why does it make sense that you take a local feature, something that encodes the local properties of a certain 3D coordinate, and then what information could that position possibly store that allows you to say something about how far you have to march along a ray to find a surface? And the key insight here is that there exists a function that maps every 3D coordinate to the step length that you have to take at that 3D coordinate. And that function is called the sign distance function. And it's actually very simple. What the sign distance function does is it maps every 3D point to its distance to the closest surface in the scene. So for instance, if you hold your finger up in front of your face and you consider that point like at the tip of your finger, then you can imagine that if your arm wasn't in the scene, right, maybe the closest point, the closest surface to that point is probably your nose, right? So now this function, the sign distance function, takes that 3D coordinate and basically maps it to its distance to your nose, because that's the closest scene surface. And you can convince yourself that if you have a ray and you march along the ray always according to that value, so to the distance to the closest scene surface, then not only will you eventually arrive at the surface, but also you will never step through a surface. You'll never skip a surface by accident, because you're always taking the step that is the distance to the closest scene surface. So what we're going to do is we're going to iterate this algorithm for a few times. So we're basically going to take lots of steps along each ray according to this value that we're predicting. And then the final iteration, we're going to call our estimate of the intersection of that ray with the geometry of the scene. And then we can sample our scene representation a final time. And now that will give us a little feature vector again, right, that describes the local properties at that point. And this time we're going to just translate it into a color with another neural network. So super high level, what we're doing is we're placing a camera, and then we're shooting rays. And for every ray, we're finding the intersection of that ray with the geometry of the scene. And then we ask, what is the color of the scene at that point? And then for every ray, for every pixel, we can then predict a color. And that is now what allows us to train this whole thing end to end just with images, because at the end of we've basically built a renderer that allows us to render our 3D scene representation from arbitrary perspectives. And now, just to, obviously I skipped lots of detail, but just to give you an idea of what kinds of things we can do with this by combining machine learning with 3D structure. One thing that we can do is we can take a single image of of simple 3D scenes. So for instance, right here, you can see this car and this chair, and you can see these single images, right? And from that single image, we can infer a 3D representation of that object. So we can go from this single image of this car to a 3D reconstruction of that car. And then we can render that 3D reconstruction from arbitrary camera perspectives. And at the same time, we also discovered the geometry of the underlying scene without having any kind of supervision for that geometry. The only thing that we have are images, but because we have built this, this representation plus this render that model the 3D structure of our world, because we have done that, our model also basically for free discovers the 3D structure of our world. And so, as I had mentioned, you can render this as at arbitrary perspective. So you can train this model at one resolution. This one was trained at a resolution of 128 by 128. But then at test time, you can render it out at much higher resolutions, like 512 by 512. And this weirdly colored image that you can see on the left here, these are the surface normals. So that's basically the color tells you what the orientation of that surface is. Just to highlight this point about 3D structure some more, we talked initially about convolutional neural networks not understanding 3D structure. And here you can see what that means. If you try to build a model that uses convolutional neural networks to map images to images, and then you try to train that model for rendering novel views of an object. And then at training time, maybe the only views that you're seeing always have the same distance from the car, but then at test time, you want to zoom in. That does not work at all because the convolutional neural network does not understand 3D structure. While with the model that we built, even though at training time, we have never seen an object up close, at test time, we can just move the camera closer and render it from up close. And we can also turn the camera on its head. So that's cool. And then you can also represent like simple room scale scenes. So this room was also generated from just a single observation that basically saw these two cars standing in the room. And afterwards, we can walk around in the room that is reconstructed from just a single image. And on the right-hand side, you can see the depth map, so the distance of each of the pixels to the camera. And on the left-hand side, you can see the images. And of course, these are all very simple scenes, right? And like very low resolution and so on. But nevertheless, I find it extremely fascinating that we're literally moving through a neural network, right? This scene is literally parameterized. It's stored in a little neural network that is rendering the scene, which is kind of crazy. Cool. So this paper that I just discussed, we wrote in 2019. Since then, this is one of the hottest areas in computer vision, and there has been lots of amazing progress. So there's this paper that some of you might have heard about. It's called NERF, Neural Radiance Fields. This was done by Mildenhall et al. At ECCV in 2020. And NERF basically proposed a slightly different render. Like I discussed this render that marches along array. NERF, the renderer works slightly differently. It's called a volume renderer. It's very cool. They make a number of other contributions that allows them to fit high frequency and to also model view-dependent effects like reflections and stuff like that. It's a really fantastic paper, and the results speak for themselves. I mean, the thing that you can see there, right, by overfitting on a single scene, so instead of just getting a single image and then inferring a 3D model, you get lots and lots of images of a scene. And then you can reconstruct this photorealistic representation, and you can render it photorealistically from novel perspectives. And this is very exciting. So many people that are interested in rendering novel views of scenes for VR or augmented reality, or even just for computer graphics are very excited about this. Similarly, there's this paper IDR, same kind of effects. The thing that you can see here is also rendered by a neural network. And then on the front of inferring these representations from few observations, maybe just a single image, there's this paper called PixelNerf, which also allows you to infer these 3D representations from just a single image. But really, since then, like a lot has happened. There's literally hundreds of papers every year on this topic, several papers per week. And there has been lots of progress on this front that really has pushed what's possible. It's very cool. Okay, so let's see, how much more time do we have? A little. Okay, so just key insights. Basically, the key insight here is 3D structure is good. If you don't have 3D structure, then you cannot hope to learn the things about the world that you would like to learn. And in order for our neural networks to understand the world, you basically need to tell them what 3D structure looks like. Okay, so let's talk about a problem. So far, I've basically talked about all the things that are great. There is a little problem with this though. So in this realm of trying to train these things to generalize across things, so to learn something about our world, which is this regime of basically trying to reconstruct things from very few observations. Maybe I show you a single image, and from that single image, you can understand the 3D structure of the scene. We want to build neural networks that can also do that. You show them a single image, and from that single image, they understand the 3D structure of our scene. So what, from all I've talked about so far, like that should be possible now, right? What's the problem? We now have these 3D structured neural scene representations. Great. Why can't we take an image of a real scene, like a real image, and from that single image infer this 3D structured representation? There's a few problems with this. So currently, as you might have noticed, these kinds of models are trained on these very simple data sets, right? Like on single objects or few objects, very structured, kind of not great. But as I had mentioned initially, like what we would really rather do is like training this on something like ImageNet, like a huge data set, you know, real images, real scenes, and then really doing this at scale to really learn from like large data sets, how does our world look like in 3D? And unfortunately, that moment is still outstanding. We haven't done that yet. And there's a few reasons for this. One of the reasons is actually this neural renderer that I had just mentioned. So the neural renderer that I had just explained to you roughly has one big problem. And all of the neural renderers for all of the different representations that I had shown you have that problem, which is that it's incredibly slow and incredibly costly. Just to basically, yeah, go for it.
Oh, one question.
Yeah.
How do you reason about the implicit function representation? In traditional CNN, we can trace the low-level features, example, edges up to higher level features. How can we find structure semantic meanings from the parameters of implicit function?
That's a good question. With semantic meaning, do you mean something like, could you clarify a little bit more what you mean by semantic meaning?
Yes, let me see if they will respond.
But maybe I can talk about this a little bit anyway. So like, yeah. Let's say, okay, so the question is, how can we take these representations and how can we, I guess the question is, how can we actually extract this semantic information from these representations? And the answer for that is has several different aspects. So the first thing you can do, as I had mentioned, this function at the end of the day, when you're done training it, maps a 3D coordinate to whatever is at that 3D coordinate. But that thing you're mapping to is not a color or not just geometry. It's actually this feature vector, right? And so it turns out that that feature vector stores pretty rich information about the 3D scene. And you can imagine why that kind of would be the case. But long story short, what that allows you to do, for instance, is you can take that feature vector and in a with very, very few labels, you can learn a function that takes that feature vector and, for instance, translates it to a semantic label. So instead of predicting the color or instead of predicting like a step length, you can now predict the semantic label of that 3D point. So you can say, this is the leg of a chair. Or you can say, I don't know, how far is this thing away from something, or what material is this made out of? So this feature vector is very, very versatile. So it allows you to encode whatever information you so wish. Another perspective to take is that the weights, so the parameters of this neural network itself, right, encode information about the scene. So for instance, what you can do is you can take those weights and you can learn a classifier on top of them, right? Because those weights basically, in this little simple example that I had shown you, encode whether this object is a chair or whether it's a car or whether it's an airplane whatsoever, right? So you can take these weights and just train a classifier on top of them with extremely few labels. In fact, imagine something like you probably have to label on the order of maybe 20 of these objects. And then from these 20 labels, you are able to learn a classifier because you have already learned the 3D structure of these objects. I hope that answers the question.
Thank you. Yeah, it should be fine until I get a clarification, but we can continue. We can continue.
Cool. I think I don't have that much time anymore anyways. So actually, I'm gonna probably just give you this idea like very briefly. And the reason I think this is important because it relates to all of these representations that you may see, and I think you might come across them in the future. Like there's a lot of work following NERF these days, especially. And this is maybe an important piece to understand. So the renderer in all of these representations works by having this ray, right? And then invariably, what happens is you sample hundreds of samples along the ray. That's what you need to do for rendering, because intuitively for rendering, when you shoot a ray, you need to find the surface. And there's no other way than to find that surface other than just sampling your representation at all of the points along the ray, more or less. Okay, so what that means is we have hundreds of samples along a ray, and for each of these samples, we have to query our 3D scene representation, which could be a neural network or it could be a voxel grid or whatever. And then, right, like for each of these points, we then get like a feature or we get whatever is there, and then we have some kind of algorithm that figures out the color that that ray is observing. And the problem with this is that it's incredibly expensive. And when I say incredibly expensive, what I really mean is, so this is a video rendered by PixelNerf, which is really fantastic work. So I encourage you to check it out. But a single frame of this video takes 35 seconds to render. And it takes 24 gigabytes on a GPU to render the single frame. And that's not great. What that means is that training this thing at scale is basically not feasible. And we had a paper at NeurIPS this year, and I'm just going to give you the high-level idea. The high-level idea is another thing you can do, and it's kind of like striking a slightly different trade-off, is to realize that the thing that you care about at the end of the day is the color of a ray. You don't actually care about, for the purposes of rendering, what is at like all of the points along the ray. You just care about the color of the ray at the end of the day. And that function that maps a ray to the color it observes is called a light field. And we have a paper at NeurIPS this year where we basically, instead of parameterizing a 3D scene via mapping a 3D point to whatever is at that 3D point, we parameterize the 3D scene via a function that maps a ray to whatever is observed by that ray. And what that allows you to do, it basically allows you to do rendering in real time, and with only evaluating your scene representation a single time per ray. And that gives you a very, very significant speed ups and memory savings. But I think I want to end this talk by something that is maybe slightly more by a final paper and a final application that is really cool. So we've talked about 3D a lot, but the concept, some of the concepts we just talked about are actually very applicable to other modalities as well. So for instance, right, let's talk about images. What are images? Images are grids of pixels. That's how they're currently stored, right? An image is basically a grid of pixels, and for every pixel you have like a color, right? Then what is audio signals? Audio signals are grids of amplitudes. You take your time axis, right? You discretize it into a grid, and then for every time point, you store an amplitude. And 3D shapes are often point clouds or voxel grids, which we already talked about. So now the thing is, it turns out that this idea that we just discussed of parameterizing a signal, a 3D scene, as a function, as a continuous neural network that maps a coordinate to whatever is at that coordinate, is applicable to any signal you can think of. any signal can be represented in this way. So for instance, for 3D shapes, like this little bunny here, you can parameterize a 3D shape as a function that maps a coordinate to, for instance, the occupancy. Like, is there something at this coordinate or is there nothing at this coordinate? And as I had mentioned, this has all these benefits of being resolution independent. It's like quote unquote infinite resolution. The memory you require scales with the complexity of the signal, not with the resolution. And it neatly integrates with all of these machine learning tricks that we have. And so some time ago, we basically tried this out and we said, okay, so what if we want to represent arbitrary signals with these neural networks? And we tried encoding images in this way and shapes, like this room scale scene, right? This is a room maybe similar to the one that you're sitting in, and then audio signals on the right. And what we found is that with value neural networks, which is kind of the default neural network architecture, this does not work at all. And maybe more damaging still, when you try to parameterize solutions to partial differential equations, which seems like a big jump, but let me just talk about what that means in practice. So imagine, for instance, like the way that audio signals propagate in your room. Audio propagates as a wave, right? And the partial differential equation determines how audio propagates through the room that you're sitting in. And so partial differential equations are basically the language of physics. They determine how many physical processes happen in our world. And it would be really important that whatever kind of representation we're building of our 3D world is also capable of having at least an approximation of the solutions to partial differential equations. But it turns out that value neural networks can't do that either. And so we had this paper at NeurIPS 2020, which was called Implicit Neural Representations of Periodic Activation Functions, or short SIREN, Sinusoidal Representation Networks, where basically we take the ReLU nonlinearity and basically we replace it with a sine activation. So instead of a ReLU, you have a sine. And a long story short, what that allows you to do is it allows you to fit basically any signal you care about perfectly. And this is actually, like, I'm going to skip the rest of this, how this works and so on and so forth, because I just want to give you the, basically, I want to leave you with two things. One is maybe just to give you a feeling for what that actually means. Here you can see a room that is encoded in the weights of a neural network. So this room, again, is encoded in the weights of a neural network. And on the right-hand side, this what you see right now is the room encoded in this neural network with sinusoidal activations. And you can see it's a very high acuity, right? It looks pretty good. On the left-hand side, you can see it encoded with ReLU nonlinearities, and you can see there's lots of detail missing. So that's cool. Yeah, and it's also tiny. So like the whole neural network takes 1 megabyte. So you can store this whole room in 1 megabyte, which is cool. But this is the key takeaway. So you have maybe seen lots of research recently that uses this exact concept that I just talked about of parameterizing a signal via a neural network. So for instance, maybe some of you have seen StyleGAN v3. That's this image that you can see here on the left is generated by a generative adversarial network. So a neural network that generates images. StyleGAN v3 parameterizes images exactly the way that I just told you. So StyleGAN v3 does not use convolutional neural networks anymore. It uses a fully connected neural network that maps a 2D pixel coordinate to a color. And that's a very significant advance, because this means, for instance, with all the things we've learned in the past 45 minutes, this means, for instance, that you can sample this image at any resolution. You can just sample this at twice the resolution. The neural network that parameterizes this image is resolution independent. Then there's also work on parameterizing 3D generative models. So in the center, you can see like 3D faces. This is a GAN that generates faces, just trained with 2 images. And then we have a paper forthcoming that uses representations like this for robotic grasping as well. So there's lots of applications where this is exciting for. Long story short, neural scene representations, that's cool. These are already useful in downstream applications. And I am personally convinced that they will be useful going forward. And there's going to be lots of applications that will benefit from these representations. There's, of course, lots of problems we haven't solved yet. So for instance, right, like if you look at this image of a dog, the kind of understanding that you have of this image far, far evades anything that we have right now, right? If you look at this image, you know how big the dog is, you know, because you can see the little tennis ball at its feet. You know how the grass would feel like if you walked over it barefoot. You know how the dog would feel like if you would pet it, right? You know that the dog is kind of looking somewhere because someone is drawing its attention. You know that there's trees in the background because you can see the light and the shadow play on the lawn, right? All of these things you infer from the single image, and we are nowhere close doing any of this. Like, this is very, very far away, and this is an extremely exciting research direction. And I'm gonna skip the rest because I think we are out of time. But the key idea of this research direction is we want to learn these scene representations in a self-supervised manner just from looking at images and videos. And then on top of these representations that we learn, we want to apply them to different applications across computer science, be it vision, graphics, robotics, and so on. And that's it. Thank you so much for paying attention. I hope it was worth your time. And yeah, if you have any questions or any kinds of things, please feel free to ask.
Thank you so much, Vincent. This was an incredibly informative presentation. Super interesting. We do have a few questions I would like to ask you. One question I received, why not use moving images or movies and use optical flow to segment 3D objects as training labels, or use stereo images such as IMAX AR to find 3D structure?
I'm sorry, I didn't get the second part, IMAX?
Yeah, IMAX, AR, IMAX.
Got it. So the question is, why not use movies? And I don't actually know what IMAX AR is, unfortunately. But the question is, why don't we train movies and then use optical flow to basically get an idea for what objects are and use that as additional supervision? Actually, I think that's a great idea. And this is something we're looking into. So it is indeed true that if you want to learn about objects in our world, then one principled way of doing that is to, first of all, you have to define what an object is. One reasonable definition of what an object is to say something that moves rigidly. So anything that if you tap it, all the points that move rigidly belong to one object. So that's a very good definition. And indeed, it's perfectly reasonable to look at videos and then use these scene representations to learn 3D structure and to supervise this in addition with this notion of things that move together have to belong together. So now the question of why not use optical flow, that's a little bit more subtle, because optical flow is not something you can just measure. Optical flow is something, of course, you have to, you need two frames and then you need to compute optical flow. And you can do that with classical methods that are just like an algorithm that someone thinks up. And that, however, is not super robust. So the state-of-the-art methods for optical flow are actually learned and trained. And the thing then is that that means you need supervision for that again, or you need to train it separately and so on and so forth. And maybe one thing you might want to do is you want to keep this property that you want to be able to learn these 3D representations really just from looking at video. So it is a little bit more subtle if you want to use optical flow or not. But it's definitely a good idea and definitely something worth investigating.
Thank you for answering that, Vincent. And then last question I received, if we wanted to read up more on these kinds of neural networks, are there any books or articles you would recommend?
Yes, that's a great question. So there are, I have just written a review article together with colleagues at Brown that will come out in the next few weeks. I'm definitely gonna tweet about it, and it's also gonna be on my website. And that is gonna be a review on neural fields, which are these kinds of architectures. Other than that, on my website, you can, of course, find all my papers. They're all free to download. You don't need a login or anything like that. And then I also have on GitHub, if you look into the news section of my website, there will be a link to my GitHub. And on my GitHub, I have a reading list, which is called Awesome Implicit Representations, which is a big reading list with resources on these kinds of representations. And that has both a few talks by me, but also by other people that do research in this area, lots of papers in this area, and then also links to collabs, which are basically interactive IPython notebooks, Python notebooks that you can run in the browser without needing to install anything. In fact, Siren, this paper on that I talked about last, has such an interactive notebook where you can actually train one of these networks yourself in the browser without doing anything on your local computer. But also, if you can't find stuff, feel free to ping me on my email address.
Awesome. Thank you so much again, Vincent, for taking the time today to speak with everyone. And thank you all for attending this First Friday lunch this month. So thank you all again, and have a great rest of your day.
Thank you. Thanks for listening in. Have a great day.